Hey y'all, welcome back to Coding with Minmer. On today's agenda, we're going to tackle a LeetCode classic 236, lowest common ancestor of a binary tree. After that, we'll go over an actual variant of the original question where you'll be given an N-Ary tree instead of a binary tree. Okay, let's read over the problem statement. Alright, so we're given the root node of a binary tree and we want to find the lowest common ancestor, or in other words, the LCA, of the two given nodes P or Q in the tree. Okay, so taking a look at our example over here, we're given 0 as the root, and here are the two given nodes where P points to node 4 and Q points to node 6. That much is clear, but we have one very important question. What exactly is meant by the lowest common ancestor? This right here is a technical definition, so I'm going to skip reading it, but thankfully the very definition of LCA is fairly self-explanatory by its name, lowest common ancestor. We'll learn what this means through an example and ask a series of questions. First question we want to ask is, what are the ancestor nodes of, let's take node Q? Weirdly enough, node Q is an ancestor of itself. This is just the rule, and if you don't believe me, you can see it here in the LeetCode description. Okay, we go upstream to node 5. It makes logical sense that this node is going to be an ancestor because it's connected to the descendant node 6 by this edge. On that note, if we keep traversing upwards, we'll encounter node 2 as an ancestor, as well as 1 and 0. What about node P? If we traverse upwards, then we'll encounter ancestors 4, 2, 1, and 0. Great, so we've identified all ancestors. Next, we'll ask the question, what are the common ancestors? So, if we previously discovered that all of these nodes belong to either P or Q, which one of these are ancestors to both P and Q? Clearly, it's not going to be node 7 because it's not an ancestor to either. It's not going to be node 5 because although it has Q as a child, it does not have P. However, nodes 2, 1, and 0 all have P and Q as descendant nodes. Lastly, what is the lowest common ancestor? Well, among these three, we have enough IQ to know that it's going to be node 2 because it's lower down than nodes 0 and 1. Oppositely, it's node 2 because it's the first common ancestor we encounter on the way up. Ultimately, we're left with node 2 as our answer, and that's what we'll return in our function. Fantastic. This is starting to make more sense. This is an example where both the nodes P and Q are in different subtrees. They were split by the lowest common ancestor, node 2. But here's some food for thought. What happens if we assign P to be at node 5 instead of node 4? And thus we are in the same subtree. Well, going through the same series of questions, we're going to ask, what are all of the ancestors to either one of these nodes? Well, it's going to be these. Next, we want to ask, what is the common ancestor to both of these nodes? Well, we can go ahead and narrow it down to these. And lastly, what is the lowest common ancestor? Well, it's actually going to be node P itself. It has itself as a child, as well as node Q as a child. Once again, if we climb upwards from node Q to node P, or from node P to technically itself, then we'd eventually encounter the lowest common ancestor. And if this doesn't make sense to you, then you can go ahead and reread this sentence right here. With that said, we now understand the premise of this problem, but how do we approach this in a more programmatic way? To answer this, we'll think back to the previous two examples and realize one thing stood out to us. We somehow need to traverse upwards in our tree. That way we can find the lowest common ancestor. Is there a tree traversal algorithm to do such a thing? Lucky for us, there is. Post-order traversal is a tree traversal that was designed to process nodes from bottom up. This policy is abbreviated to LRC, where on any given node, take node 1 for example, we'd visit the entire left subtree before backtracking to recurse down the right subtree, and on the backtrack, we'd get around to processing the current node. Okay, so we're confident that this tree traversal is the correct choice, so let's YOLO and dispatch this DFS call and practice some reverse engineering. We know the goal is to return node 2 as the resulting LCA, so let's do everything we can in the logic to ensure this. Okay, so let's go ahead and start at this root node where by order of LRC, we want to recurse down to the left subtree first. Here we meet our first base case. There's literally nothing here. So in this case, why not return a null pointer to indicate that there was indeed no object? I'm sure this will be helpful for node 0 on the backtrack. Next, we're going to recurse down to the right subtree to node 1. Here we'll repeat our LRC instructions where we'll go down to node 2. Then we'll do the same thing and go down to its left, node 4. On node 4, we could follow instructions and visit its left subtree, but why would we? Node 4 itself is one of the key nodes that we're looking for. We think ahead and we immediately would like to return node 4 itself so that on the backtrack, node 2 can have all the information it needs to know that it's the LCA. Back up to node 2, we're going to go down to its right subtree, node 5, where we're going to go to its left child. Nothing is there, so remember, we're going to go ahead and return a null pointer to indicate that we found nothing. Then we'll go down to node 6, and hold on, we found the other node that's important to us. We hit the jackpot. Like before with our key node P, we should also return the key node Q. It will be returned to node 5, not our eventual LCA node 2, but whatever, we can make this solution work. One thing before we move on in our example is note that we never visit node 7. Here, that's okay, because the moment we visit either node P or node Q, we know that we need to immediately return it. Back at node 5, what do we even do? Well, let's look at the information we have. We know for a fact that we found nothing in the left subtree, but we did find a key node here in the right subtree. So why not continue returning node 6, thereby carrying it in this upward traversal and ensuring that when we backtrack to node 2, we have even more information and context at our disposal. Remember, knowledge is power. Alright, so we visited both the subtrees of node 2, so let's get around to processing node 2 itself. Here's what we know if we found one of two nodes, either P or Q, in the left subtree, and we found the other key node in the right subtree, then doesn't that make node 2 the lowest common ancestor? Once again, we're going from bottom up. So the moment we encounter a node that shares the same path as its two descendants, P and Q, then the node itself must be the lowest common ancestor and will return the current node. On the backtrack to node 1, post order tells us that we need to recurse down to node 3, where we won't find anything, so we're just going to go ahead and return a null pointer. Back at node 1, we know we found something to its left, and I'll remind you it's our answer, but nothing on its right. Here everything becomes clear. If on a given node we found exactly one key node, whether it be P, Q, or the LCA itself, we'll simply return it. We can keep carrying these nodes upwards until we eventually return it as our answer. So on node 0, we face a similar situation. We found nothing to its left, but we did find something to its right. We'll return that something to its right, and we're done with our function. Ultimately, node 2 is indeed the lowest common ancestor we're looking for, and that's what we'll return as a result. To summarize our decisioning on any current node, when we found key nodes in both subtrees, like here at node 2, then we're going to return the current node itself. When we found only one key node in either subtree, for example here, then we're just going to return that one key node. And if we found 0 key nodes, then we'll just return null pointer. Just a hint, this will be very helpful for the variant after this problem. Anyway, the time complexity is a singular big O(n) because we only dispatched one traversal. The space complexity is also big O(n) because of recursive stacks. It's big O(n) in the worst case that we have a linked list as a tree. Alright, let's get to coding. Okay, so let's define the method signature for our post-order DFS call. We'll call it DFS, and it'll pass in the same parameters. Alright, what are the base cases? If the node is null pointer, we'll simply return null pointer to indicate that we didn't find any key nodes. However, if we found key nodes P or Q, and we know this if their integer values match what we're looking for, then we'll return the key node upstream. Next up, this is post order, remember? So let's process the left subtree, which on the backtrack will potentially get a key node. After that, we'll recurse down the right subtree. It might return a key node as well. Now we get around to processing the current node. There are many possibilities. What if we found a key node in the left subtree and a key node in the right subtree? Well, this must mean that the current node itself is the lowest common ancestor, so let's return it. Otherwise, what if we only found one key node and it was in the left subtree? Well, we'd return that. If the only key node we found was in the right subtree, then we'd similarly want to return that. If we found no key nodes, we'll return null pointer to again notify the parents that we're empty-handed. The very last thing we'll do is call our helper DFS function, and we're officially done. As you can see, the variant is just an extension of this problem, so let's take a look. Okay, so for this variant, instead of a binary tree, we're now given an N-Ary tree in its place. What's an N-Ary tree, you ask? Well, an N-Ary tree is a tree where each node can have up to n children. Taking a look at our example here, we can see that node 8 has 3 children, node 13 has 4, so forth, so forth. This has implications on our node class. It no longer just has pointers to left and right children as hard-coded fields. Instead, it'll have a list of all of its children. I also won't go over the definition of LCA again, but I will spoil what the resulting LCA is in this overwhelmingly huge example. It happens to be node 4, since it's the lowest node that has both P and Q as its descendants. Thankfully, just because a node can have n children, it doesn't really affect the essence of how we find the LCA. We're relieved to have solved the original LeetCode problem because we can reuse the bulk of the logic from before. There's 2 pieces of information in particular that carry on from the OG problem. One is we're still going to dispatch a post-order traversal because we want to solve this with a time complexity of big O(n). Therefore, our tree traversal workflow will be very similar, except when we recurse from any given node, let's take node 2 for example, there's no longer a left and right subtree to call DFS on. Instead, it's a list of subtrees. So we're going to loop over each child to recurse down. 2. On any given node in our N-Ary tree, we still only care if on the backtrack from all the children, if we found 2 key nodes, 1 key nodes, or 0 key nodes. Remember, the key node can either be node P, node Q, or the LCA itself. With this context in mind, let's just go through an example. I'm not going to get into the nitty-gritty details since we're all post-order pros by now, so let's skip to the interesting part where we're going to end up at node 13 because it has one of our key nodes as its children. Here at node 13, we're going to recurse down all 4 of its children. It's obvious that these 3 are going to return a null pointer, except for this one that has our key node. Like the OG problem before, we want to track how many key nodes we have on the backtrack to any given node. Before, we could manually count the number of nodes because we only had 2 children, the left and the right subtree. But now we could have n subtrees. There are many ways to count the number of key nodes, but for me, I'll choose to initialize a local list on each node on the recursion downwards so that on the backtrack to any given child, if we have a key node, like this one here, then we can simply push it into our list. As for the rest of our subtree, null pointers just indicate to us that we didn't find any key nodes, so we don't need to do anything. Ultimately, we found 1 key node in our list, so let's return it upstream to node 10. On the backtrack of node 10, we're going to add the key node of 14 that we found into a list. And since there's no other subtrees to recurse, then we'll return the singular key node to its parent node, node 8. Here we have the same situation. We only found 1 key node in our list, so we'll return it as well. Now we're on the backtrack of node 4, and we already have a list initialized. On the backtrack of node 8, we luckily already did that example, and we returned node 14. Great, we can add it here in our list. On the backtrack of node 7, we would have gotten a null pointer, so we don't push that into our list. And lastly, on the backtrack of the last child node, node 9, we end up returning this node itself since it's a key node. Let's go ahead and push that into our list as well. Now with this information in our brains, we get deja vu because this was an exact situation from the previous problem. We found 2 key nodes, which means one of them must have been P and the other must have been Q. Therefore, in this case, if we ever have 2 nodes in our list, we'll execute an if statement to return the current node itself, node 4. Okay, so we backtrack to node 2 and we'll add node 4 into our list. Then we'll continue recursing down all the other subtrees, so sure, let's go to node 5. Here we'll go through all of its children, but it has none. Because the list of key nodes we tracked is empty, then we're going to go ahead and return null pointer. This signals to upstream that we have found nothing useful. Now we'll traverse down to the last subtree to node 6, where the same deal happens. It has no children, so since our list holds 0 nodes, we'll go ahead and return null pointer as well. Finally, we process node 2. We peek into our list and realize that we have 1 key node. In this case, it's the LCA itself, so we'll return it upstream to the parent. We're now on node 1. We'll add the new found 4 into our list and we'll recurse down to node 3. I'll tell you right now, we're just going to get back a null pointer Finally, we get around to node 1 where we only have one key node in our list. Let's go ahead and return that. And just like that, we're finished. Node 4 is our answer, and that's what we'll return. If you want to verify it visually, here it is. The time complexity is going to be big O-N, and the space complexity is also big O-N. Let's code. Alright, so what changes in our implementation? Thankfully, not too much, so let's go over them. The base cases are gonna remain the same, so we'll leave those unchanged. Next up, we no longer have a left and right subtree, so let's remove that. Instead, we want to initialize our local list of key nodes that we find. And then write a for loop over each of the children's subtrees. On each iteration, we'll recurse down and potentially get back a key node. If we found a key node, and we know this if it's not null pointer, we'll push it into our local list like so. Now when we've backtracked from all children and our loop has ended, we'll have to change our if statements here. Specifically, if we have exactly 2 key nodes, then we must have found the lowest common ancestor. We'll return the current node. Otherwise, we need to check in our list if we only found one node. This means that we only need one if statement clause. If this is the case, then we'll return that single key node, which can be accessed at index 0. Lastly, we'll still return null pointer in the case that we found nothing. And that is the code. Thank you all for your support. Go spread some positivity in the world.